chair, and I'm a regulatory specialist. I think maybe Anton, Yassi, Haley, do you want to do quick intros?
Sure. I'm Anton Hasbrook. I'm a mechanical engineer with Central Nebraska Public Power.
Excuse me, Yassi Saba. I'm an electrical engineer with Burns McDonnell.
And Haley Kessel. I am the Director of Regulatory Affairs with Current Hydro.
So we have a super packed agenda today covering all things dissolved oxygen, from regulatory landscapes and how it kind of plays a part in relicensing, to mitigation strategies and technologies, to kind of a case study of how the rubber meets the road and how Eagle Creek is actually implementing those mitigation measures at some of their facilities. But before we get into the meat of today, we have a few announcements. First and foremost, we want to thank everyone who submitted an application for the Rising Star Award. The application deadline has passed, so we're actually in the process right now of doing the peer review for those applications. The next step is the finalists from the peer review committee is going to be sent to NHA's Board of Directors Nominations Committee, where a finalist will be selected. That finalist will be notified in August and then formally announced at Clean Currents in October. So we'll keep folks up to date kind of as we move through that process. Couple NHA events coming up. The first is going to be the Northeast Regional Meeting. That's taking place in Fitchburg, Massachusetts from July 22nd to 24th. Flow members get 50% off registration. So if you are attending, you can use code FLOW. It's in all caps, FLOW. You'll get 50% off. There's going to be 2 flow events at the regional meeting. This is actually the first time that we've had flow events at a regional meeting. Typically, they're for national events like Waterpower Week or Clean Currents. So the first one is going to be on that Tuesday, July 22nd. There's going to be an early career professionals lunch right before the facility tour. So you'll have time to do both events. But that will be a great way to kind of get your feet wet with networking if this is your first conference and start meeting some of the folks in our industry. There's also more of an informal after-hours social happy hour following the NHA happy hour on July 23rd. It's no host, so NHA won't be hosting it, but it is a dedicated space for people to continue networking after the happy hour, and it's open to all members of the conference, not just flow attendees. So again, a great way to meet other people. We also have Clean Currents coming up in October. It's in Pittsburgh, Pennsylvania from October 14th to 17th. Same thing, flow members get 50% off. For this, if you are attending and you want that discount code, you can reach out to Ellie with NHA and she can help you through that process. This is also a great justification for your attendance at the conference. If you have to justify what value it would be for you to go, having reduced registration can help in that process. There's a variety of events at Clean Currents, including some flow events, so stay tuned for more information on that. And I think that's all the announcements we have. So kind of as we go through the program today, if you have questions, feel free to put them in the chat. We're going to have 3 series of presentations, and then we'll have a Q&A at the end. So I'm hoping all the speakers on the phone are able to stay and help work through that Q&A at the end. But for members on the phone, again, chat your questions, but please mute yourself during the presentations. And then when we get to the Q&A, feel free to turn your cameras on and you can ask your questions verbally if you would like. And then for the speakers, right before you get into your presentations, we're kind of hoping you can give us a career snapshot. So 30 seconds to a minute of your career journey and an overview of how you got to where you're at today. And then feel free to roll right into your presentation. So up first, we have Jim Gibson and Ty Ziegler with HDR. Jim is HDR's National Hydropower Relicensing Business Class Lead, and Ty Ziegler is HDR's Environmental and Regulatory Manager for the North Carolina and Georgia offices. They're going to be discussing what dissolved oxygen is and how it plays a role in relicensing and then ending up in license articles. So Ty and Jim, I'll turn it over to you.
Okay. I'm going to start. So again, my name's Ty Ziegler with HDR, and for my little snapshot, I started my career with a Duke Energy, which is a big electric utility in the Southeast. And I did a wide variety. I'm an environmental engineer background and did a wide variety of engineering or environmental engineering projects for their power fleet, which included hydropower. And I really, of all the projects I worked on, I really gravitated towards hydropower projects. And ultimately, that morphed into me leaving Duke Energy to join a consulting firm that was a hydropower specialist. And that firm ultimately what was bought by HDR a number of years ago. But I've maintained kind of that connection to the hydropower industry throughout that time. My particular specialties are water quality and aquatic habitat, so fish habitat downstream of hydropower plants. And I do a lot, I'm involved in a lot of different relicensing, hydropower relicensing studies that involve both water quality and aquatic habitat. So I'm going to share my screen. Hope this works okay.
I can see it.
You can see it? Okay. So Jim and I are going to work through the first part of this presentation. Let's see if I can advance here. Okay, so there's me and Jim. So I'm going to start with what is dissolved oxygen. So it's a measure of how much oxygen is dissolved in the water. And it's typically, you will see it expressed in terms of milligrams of dissolved oxygen per liter of water. So, and in natural environments, it's absorbed, dissolved oxygen is absorbed into the water body from the atmosphere, and it's also released by aquatic plants as part of the photosynthesis process. So that image that I'm showing in the upper right, those are air bubbles. So the air bubbles itself, that's not dissolved oxygen. Dissolved oxygen is oxygen that's actually dissolved in the water column. So now it's coming from those, in this case, it's that oxygen is being transferred from that air bubble into the water, but having lots of air bubbles does not necessarily mean you have lots of dissolved oxygen, because it's a function of also temperature and pressure and how long that water bubble is in the water column to transfer oxygen into the water. So it's important because aquatic organisms use it as part of their respiration and metabolic processes. And it's a very important indicator of water quality and a water body's ability to support aquatic life. So, with the Clean Water Act, the EPA implemented water quality standards nationwide. And so, and the standards apply to the various states, tribes, and US territories. And states typically require both temperature and DO standards associated with hydropower operations. And it can be different whether you're talking about streams or reservoirs, and it's also dependent on the designated use of the water body. So for example, I'm showing just in South Carolina, and many states have similar criteria, but it can vary from state to state. So states will have a temperature criteria, not to exceed a certain degrees or a certain temperature rise. And likewise for dissolved oxygen, they'll have a standard for, not less than a certain milligrams per liter on an average basis. They'll have an instantaneous, so at no time can it drop below 4 milligrams per liter in this case. And if your water body happens to be designated as trout waters by the state, then that threshold increases to 6 milligrams per liter on both the average and instantaneous. So the point here is, the EPA has, and then states have implemented dissolved oxygen standards. And the reason I show that with temperature is temperature and dissolved oxygen are very interrelated. And so this is a diagram of thermal and dissolved oxygen stratification in a reservoir environment. And so what this is actual data from a project that I've worked on. So every 2 weeks we went out and we did depth profile measurements for temperature and DO, and you can see that in the look here on the right panel first, for dissolved oxygen. Dissolved oxygen started in the summer where, at the surface it was about 9 milligrams per liter, and it gradually declined down to about 2 milligrams per liter at the bottom of the reservoir. And as the summer progressed, that dissolved oxygen gradually shifted and became less in the water column. And temperature, actually did kind of the reverse, where in the early part of the season, the temperatures were not very strongly stratified. There's a little stratification where it's warmer at the top than at the bottom. And then as the summer progressed, that temperature became much warmer in the upper layers called the epilimnion, and they were still cool in the hypolimnion. So like I said, temperature and DO are very interrelated. And why is dissolved oxygen lower at depth? That's because, like I said in the previous slide, in a reservoir system, that oxygen is coming in from the atmosphere. So it's coming in through the surface, and that the amount of dissolved oxygen as you go deeper in the water column becomes less. You also have just biological processes, biological oxygen demand, chemical oxygen demand. So there are things in the bottom of the reservoir that are actually consuming oxygen, and that's why, and it's not able to replenish because it's too far away from the surface. So you get, this is a natural process, and it occurs in many reservoirs throughout the U.S. and throughout the world. Not in every reservoir. You may have certain climates that are very cold, and you don't get this thermal and dissolved oxygen stratification. But this is really typical. This is not man-induced. It's a natural process. How you measure temperature and dissolved oxygen. This is just some sampling gear. You can do this with a data sonde that you say lower over the side of a boat, and you can get discrete measurements. You can also record temperature and dissolved oxygen continuously, and so that's what this is. This is a setup where in this photograph you have a data logger, and then or a recorder, and then each one of these silver tubes is a temperature and DO logger, and they're all connected together by a data cable, and you can mount those underneath a buoy system where the data, the recorder is actually housed inside of the buoy, and then you have this cable suspended below the buoy with these data loggers. And so for this situation, we're measuring continuously every 15 minutes temperature and DO at multiple locations. It's a single monitoring location, but at multiple depths at that location. So that's a pretty typical setup for how you measure or monitor temperature and DO. Why you do this and why it's important, and I'll get to how it's related to hydropower here in my next slide. But what happens during the summer months, you get this what we call the squeeze. And so you have atmospheric, so solar radiation, your upper layers or your epilimnion are heating up, and that's actually becoming too warm for many fish species. So fish are moving down in the water column because it's too warm in the upper layer. But at the same time, remember the figures I showed where dissolved oxygen was really low in the bottom of the reservoir. And so fish, they need oxygen to survive. So they can't, they're not in the very bottom of the reservoir during the summer months, but if it's strongly stratified. And so they're typically found in this metalimnion. And as the summer progresses, this top layer sinks down and the bottom layer rises. And so that's the squeeze. So how this is related to hydropower, this is just a cross-section of a generic hydropower plant. So you have a dam here, the hydropower operating unit here on the right, and then on the left is the reservoir. And so depending on where your withdrawal zone or your opening for your for the hydro is, you may that withdrawal zone may be located at a depth where you have low dissolved oxygen. So what happens is you operate the plant and you're basically pulling lower dissolved oxygen water from the forebay of the reservoir, and you're discharging that into the tail race. And so, and that's, this is one of the things that is often studied during hydropower relicensing projects is what can the project, if this is the case, then what can the project do to help minimize the low DO in the discharge? It's a natural process in a reservoir, and so typically you're not trying to necessarily overcome the low DO in the bottom, but you're trying to either at the turbine itself or in the penstock, in the turbine, or in the tail race, trying to do something to improve the dissolved oxygen content. So, and I don't want to get too much into the, I know Voith is going to really cover this more than me, but there are a variety of different techniques of enhancing oxygen. So there are techniques where you can inject air or oxygen in the reservoir, in the penstock. You can have a selective withdrawal where your withdrawal zone maybe changes seasonally as that onset of stratification occurs. There are passive aeration technologies like weirs. For example, you could build a wall in your forebay to where the water that comes into the hydropower plant has to go over the top of a wall, and so you're basically forcing water up closer to that surface where it can pick up more oxygen from the atmosphere before it goes into the penstock. So, and there are various ways of aerating in the tail race of a plant. So, and I have this slide in here. I'm hoping Voith will really get into mechanical aeration. So this is in the turbine itself. So I'm not going to really cover this, but just suffice it to say, what we're trying to accomplish with a lot of these studies and engineering fixes is looking for ways that we can introduce more oxygen or more air or oxygen into the system rather than it just relying on the surface of the reservoir. And I think if Jim is on, Jim, do you want to cover, you have a case study in here?
Yep. Yeah, and I'll keep it pretty brief. I know there's other speakers today. Just real brief, Jim Gibson, just like Ty with HDR, sit in Syracuse, New York, and been doing licensing and permitting for some time now. Probably shouldn't admit the number of years, but really enjoy doing FERC licensing. So when we talk about DO, very few licensings do you not have some dissolved oxygen conversation. Primarily, just like Ty said, driven by the Clean Water Act, and depending on the species upstream and downstream, agencies are very interested in those DO levels, particularly depending on the downstream fish populations. So a couple things I'd point out here. Do have what I would consider a case study. It's an ongoing TLP relicensing. So don't want to get into any names of projects or names of clients here because it's still ongoing. But in this instance, a lot of conversation about DO leading into the proceeding. Two reasons. First of all, there is a robust trout population, both stocked and natural breeding trout population downstream. And although we never experienced it firsthand, we heard frequently about the sulfur odor that occurs just downstream of the tail race. So if you smell that egg smell that you sometimes get, you can run into a lot of different instances that cause that. But low DO and other occurrences or other reasons can make that occur in a tail race or a camp toward the upper end of a bypass reach. So starting from day one, there was all this talk of a sulfur odor. So that really got folks interested. So what was requested was year-round continuous DO sampling at multiple locations, both upstream and downstream, including multiple depths, just like Ty was showing. They wanted to get some pretty thorough profile readings. We pushed back on this pretty strongly because for a couple reasons. Now, here in the Northeast, it wasn't that long ago, we did not do continuous DO monitoring. I think other parts of the country have been doing that for some time now. But we would often just go out periodically and collect DO. So not only continuous, but year round. And year round is something that we don't think is acceptable, just because you get into those winter months. Not only is it almost impossible to get DO readings with ice cover, but you just don't have a DO impact because of, just like Ty was describing earlier, temperature effects. So we did push back. We did say, as compared to continuous year round, we recommended that we did some limited DO sampling, jumping down a couple bullets here, during the warmest time of the year. So we, based on historical information, we said, okay, we'll pick out 3 weeks in late July throughout the month of August. We will collect DO samples, but we're going to do it only during these times when you've got that warmer water. And this was driven by the lack of stratification, lack of a thermocline, which we already knew. Take-home message from all this is a study dispute was requested by an agency. Even in a TLP, you can do a study dispute. That led to a joint meeting. We can talk about that if folks have any questions. But at the end of the day, what resonated with FERC, not to use a pun here, but was the residence time of the impoundment. The fact that the residence time of the impoundment, I think we demonstrate even during low flow periods, was somewhere between 50 and 60 hours. It was decided that the pond could not stratify and you could not get that low DO water relative to the intake. So that was a real needle mover, and something I think that we learned coming out of those conversations, that it's worth emphasizing residence time if it's a shorter residence time in particular, even as early as the pad through some quick calculations or through study scoping. So with that, if there's any questions, be happy to cover them later. But Katie, that's all I have today.
All right. Yep, Katie, so I'm going to kick it back over to you.
Thank you both so much. And just for folks who maybe aren't super familiar with relicensing, PAD stands for pre-application document. It's kind of the kickstart to your relicensing process. But Jim and Ty, thank you so much. I hopefully either one of you or both of you can stay on for Q&A a little bit later. But if folks have questions, feel free to put them in the chat, and we'll address them in a couple minutes when we get there. So next up, we have Russell Labarca, who is the manager of hydraulic application and layout with Voith, really here to discuss mitigation strategies and tools to manage DO. So Russell, I'll turn it over to you.
Okay. So I'm going to do a quick intro for myself as well. We're located here in the hydraulic engineering group in York, Pennsylvania. So Voith Hydro is a full line turbine and generator supplier. Here in York, we focus on modernization. I've been with Voith for my whole career out of college for about coming up on 18 years now. And I'm going to turn it over to my colleague, Andrew Stordahl, to give his brief bio and also do the presentation here.
Yeah, hello, my name's Andrew Stordahl. Like Russ, we actually only started about a couple weeks apart from each other, so I've been here about 18 years as well. And I work here in the hydraulic application group, primarily focused on predicting performance and doing application layout for bids for modernization projects. all throughout the world. And so the focus today obviously is on our aeration technology and what we can do to overcome these dissolved oxygen difficulties that we can have. As Ty was mentioning, I'll quickly breeze through this because he already talked about it. We get depending on where the intake is, you can be drawing this lower oxygenated water in through the turbine, which then goes downstream, and then that causes some complications. And so what can we do to overcome this from a technical side? You can do things like trying to get mixing on the upstream side. You can add liquid oxygen. There's several different types of things, but Voith has come up with a technology that gets air into the water to help improve the dissolved oxygen as the water is going through the turbines and generating revenue. So as we probably know, there are low pressure regions within the turbine, particularly in the runner passageway. I mean, that's its primary goal, is to take this potential energy and pressure and convert it into the kinetic energy to drive the generator and produce electricity. So these low pressure regions occur on, not surprisingly, the low pressure side of the runner, just below that. So here in the runner cone, also at the exit of the runner blades, and here at the top of the draft tube. And so we use our CFD calculations to predict what the pressures are in those different locations. And years ago, came up with the idea, hey, there's low pressure here. We can probably get, that's below atmosphere, so we can probably get air into the turbine in these locations. And so 3 different ways of getting an natural aspiration into the machine were developed. Central aeration, which is quite common as a smoothing pressure fluctuations and vibrations. At part load operation, well, we can make that a little bit bigger and we can shove some more air in there. So that's an option. Also here at the top of the draft tube cone, we can add a peripheral system. So there's a little chamber with a manifold. Here it also works with axial flow machines, and that can also take advantage of that low pressure region. And Voith developed technology to actually get a distributed system. And so the air is actually going through the runner blade passageway, and then you get an advantage of taking advantage of a low pressure region, but also distributing that air throughout the entire water column. Here with the central system, it really stays in the middle of the water column. With the peripheral, it really likes to just follow the wall of the draft tube. And yes, there's secondary flows. You get a little mixing that way. But with the distributed system, across the entire turbine operation range. So at part load, when you have a lot of secondary characteristics going on in the draft tube, you're going to get a lot of mixing. At the peak, when the water is moving really nice and smooth, it's all quiet and nice, you're still getting a lot of mixing because the air is being introduced throughout the entire water passageway. And at full load, same thing. You get high velocities and a lot of drawing pressure, but you need a lot of mass flow in order to compensate for the very high flow rates going through the machine. And with a distributed system like our air rating runners, you get that distribution, and because you need to have that concentration, because it's just a mass transfer problem. And so Voith's aerating technology comes through the discharge edge of the runner blade, because that's the lowest pressure region in the entire machine. And so you get a lot of suction or drawing pressure to pull in the airflow. Because this runner, it's along the discharge edge, you get distribution radially through the water column, and obviously it's spinning. So you get it circumferentially throughout the entire water column. And so that mixing really helps distribute the air so you can get a lot of surface to air contact to get that mass transfer to happen. It doesn't block the air flow passageway. in any way because it's at the discharge edge of the runner blade, which is always there. And so it doesn't really have a meaningful impact on the turbine performance. And when you're not needing to aerate and increase dissolved oxygen. And so it is a real benefit to the operator that you don't have any problems. And so you could introduce things into the water passageway in different ways. There's all kinds of other aeration devices that insert something into the water column to get air into these low pressure areas. But they reduce efficiency when you're not aerating because you got an obstruction in the water passageway. So Voith has been doing this for a while. We have around 33, I think, at the last count, aerating runners in operation. Anywhere from about 120 to almost 200 inches in diameter. Heads anywhere from 50 to almost 300 feet in head. And a big range of output of these machines as well, from 7 to 127 megawatts. We have a few more that are out in the shop and being installed in the field as well. We also have a couple of Kaplan peripheral systems that we've put in over the years as well. And while those are a little less common because of the complication with that, we still have done that system and they're operating quite well today. And so Voith has been in this business for a long time. We've been making hydroturbines for over 130, 40 years or so as a company. And we were involved in one of the first auto-venting turbine designs at TVA's Norris Dam back in the mid-90s. And since then, we have installed a whole bunch of machines, and we've really been continuously developing this technology and making improvements. In the mid-2000s, we started doing better modeling, computational modeling by using the discrete bubble model to predict what the dissolved oxygen is going to be. So that way we can design around that and know before we build it and design it, install it, what we can expect. We have been able to increase the head at which these machines have been operating up to about 275 feet. We've combined this with minimum stream flow requirements such that we have a design out there that operates at a significantly reduced flow to comply with FERC licensing for a minimum stream flow and to add dissolved air and dissolved oxygen at those types of conditions. We've been doing more multi-phase CFD to help with our prediction process. And we've also been making other design enhancements to develop for deeper turbine settings because the relative position of the tailwater compared to the unit center line is a real driver because in terms of the drawing pressure that you have. And so we've made improvements to accommodate that as well. So into the modeling, the airflow is obviously important. The more air you get into the runner through the discharge edge of the blade, the more dissolved oxygen concentration you can improve. And so we calculate the pressure at the air inlet location from CFD. And we also need to account for all of the flow losses in the system. So considering the intake pipes and any manifolds and things like that in the head cover region, the air going through the blade passage and in the slots. And then we also have a lot of experience with the air pressures that we've calculated versus what we've measured in the field. And so we do have a little bit of a correction to take that into consideration as well, because things do get complicated when you get a air-water interface. And ultimately, we need to figure out, well, how much of this mass transfer is going from bubbles into the actual water, because that's what we really are interested in. And so the discrete bubble model was developed to predict the dissolved oxygen uptake. It accounts for the different site conditions, such as, the size of the draft tube, how far the air bubbles are going to travel, the mass flow of air, the size of the bubbles are important, the different operating conditions of the turbine, whether you have full load or the peak or somewhere in the part load region. And of course, the turbine geometry is important for that as well. And so what we do is we basically develop a little computational model of the entire passageway and track an individual bubble as it's going from the air inlet location all the way through the draft tube and up to the surface. And so that way we can integrate that for different size bubbles based upon the different operating conditions and calculate then what do we get in the tail race. And we've done this a lot of times over the years. And so we have a pretty good data set of experience. And so we're confident with our calculations. Yes.
Sorry to interrupt. Just want to do a quick time check. About a minute and a half left.
Yep. I got my last slide. Perfect.
Thank you.
All right. And so we're confident enough in our calculations that we have been making guarantees in dissolved oxygen in the tail race, assuming when we have good understanding of the water temperature and the incoming DO and tailwater levels, because those are big drivers in terms of what the system is capable of doing. We guarantee efficiency with the air valves closed, which is basically just like any other turbine. We can guarantee the efficiency while aerating because there are performance impacts by injecting fairly large volumes of air into the system. And then also cavitation performance. Injecting air into the system can help with other types of operation conditions too. I mean, just like we would have a central air admission system to help smooth part load operation, these dissolved oxygens aerating runners can also do that sort of thing too. So that is my last slide. So I think I am right about on time. Hopefully. Yep.
You are perfectly on time. I shouldn't have even said anything. Thank you so much, Andrew. And
it's all
hopefully
good. You're welcome.
You're available to stay on for a few extra minutes too for the Q&A at the end.
Yep, for sure.
Yeah, we'll be here.
Okay, good. Thanks. So our last presentation, but certainly not least, is going to be about kind of where the rubber meets the road. We've talked about what is DO, how do you study it, and let's say it ends up in a license. Now we've talked about some of the tools that can help to manage DO problems at a site. So how does that look like at an actual facility? So Joyce Foster is the Director of Licensing and Compliance with Eagle Creek Renewable Energy and is going to be speaking to just that. So Joyce, I'll turn it over to you.
Thank you. I'm trying to present my slides, so hopefully that's working. And you guys can see those, okay?
We can see it.
Oh, excellent, excellent. Just let me know if there's something wrong. So again, I'm Joyce Foster with Eagle Creek Renewable Energy. I'm Director of License Compliance. I'm physically located in Virginia, but I cover projects from Southern New York to North Carolina. And basically my quick bio is I've worked at an NGO, a state regulatory agency with water quality monitoring, and as a consultant for hydropower relicensing, and now I'm on the owner side. So I've kind of seen and done it all, I would say. And so I have an interesting perspective when it comes to relicensing at times. So I'm just going to kick off. We wanted to highlight a project, the Yadkin Hydro Project in North Carolina, a kind of an innovative approach to DO enhancement that was implemented by our CEO, who's an engineer and innovator, and challenges us every day to innovate on new things and to not do things exactly the way we might have been told to, but to question everything. So this is going to focus on the High Rock and Tuckertown facilities, this linear cove valve operation that we've been using to enhance DO for quite a few years now. So just did give you a high level of looking at improving dissolved oxygen at the project. Dissolved oxygen levels at High Rock and Tuckertown tailwaters periodically fall below the state standards in summer and fall. I know HDR kind of talked a little bit about those state standards. North Carolina Department of Environmental Quality, formerly Division of Water Quality, in our 401 Water Quality Certificate, which is a requirement that we have in our license, actually required us to do DO enhancing technology at the project. And we have a series of 4 reservoirs and dams at this project. So the High Rock and Tuckertown are the 2 uppermost plants there. And so we have to release and look at the standards at each of the tailwaters and also what we're releasing into the river downstream of our project. And the water quality certificate was very specific. It specified a Howell-Bunger valve. I don't know the history behind why that was specifically specified at the time. But when we looked at starting to implement the license, we wanted to still meet water quality standards and dissolved oxygen, but our company was interested in investing in R&D and technology to meet DO standards. So they looked at a lot of different technologies that were out there, looked at what might work, what might be suitable here at this particular project, and evaluated those at a high level. They looked at traditional solutions, prove the advantages of it being proven technology, but there were challenges, particularly with the Howell-Bunger valve related to reduced dam integrity that they were concerned about. Also, boating and fishing safety. The tailwater areas are very popular there for fishing. Impacts to recreation, potential impact to National Register historic places if that's part of your project. And also other things like long installation time and other limitations to that technology. So our folks looked at doing an alternative, and they kind of looked at different evaluations, different technologies. One of the things that they looked at and decided to go with and decided to work on developing there for the project was this linear cone valves. And so there are advantages of that. In particular, it's easy to install on existing spillway gates, utilizing existing gate motion and forces, and to adjust that valve settings. The valves can be reconfigured to self-regulate flow or vary oxygenation. It was a 20 times reduction in installation time, safer for downstream recreation, maintains the integrity of the dam. So our folks were really interested in pursuing this. So discussed it with the regulatory agency NCDQ there in North Carolina, and looked at whether this would be something they might approve as a replacement or in lieu of the Howell-Bunger valve. The challenges with this was it's a new solution. I had limited field experience at that time, and it was limited to facilities with spillways, such as many of the facilities we have at the Yadkin project. Move to the next slide. So this is just kind of a little graphic that shows you a little bit about the operational flexibility. We do have a video. We didn't have time for that today, but if anyone's interested, it used to be on our website, but apparently it's no longer there, but we can certainly give you a link to that if you're interested. So really what we were looking at doing was improving dissolved oxygen using various methods and look to meet all of the requirements in the 401 water quality certification. So I've highlighted a few things here. We did also some upgrades to generators, other upgrades, installation of these linear cone valves. And the agreement was with DEQ. Obviously, if those planned enhancements did not result in compliance with the water quality standards for dissolved oxygen, additional measures would be required. So really, what we looked at doing was during generation, we installed aerating turbines at High Rock, all 3 units there to help during generation periods. During no generation periods, we worked on operating and installing these linear cone valves at both High Rock and Tuckertown. So once all of these enhancements and were made, we did a testing with the state, and there were some challenges. There was hyper-eutrophication upstream. The DO standard there in North Carolina is a 4.0 MGL instantaneous and 5 average DO standard, daily standard. DO enhancement requirements are from May to November, and we do monitoring from those periods. And the standards had to be met during periods with and without generation. So just to kind of give you a little overview, here we have the linear cone valve was installed in this gate. This little figure of a DO boat, I'll show you exactly what that is, but that's where we do our monitoring for dissolved oxygen in tailwater at High Rock. And this is Tuckertown. The linear cone valve is installed at this gate. Powerhouse, the DO, what we call the DO boat, is installed here. The dissolved oxygen boats are kind of an interesting structures. I think this was devised from our CEO at the time. And the dissolved oxygen boats basically are a floating sensor package. So they provide the real-time monitoring of water temperature and DO. The design was revised in 2018 to improve stability and reliability during high flow events. They are occasionally removed only during the threat of extreme hurricanes, typically, or extremely high flow events are forecasted. It has the sensors, it has onboard power supply, solar powered, and batteries. The DO boats also have communications and data and onboard data storage capabilities, and wirelessly updates to our server every 10 minutes. And then the operators can also connect and view live data to the instruments at the sensors. So I mentioned that we were doing the testing. So that went on for about a season of dissolved oxygen, entire season. Looking at what those values were, testing at various operations and multiple settings, collected a number of operational data points. And I know we're getting a little short on time, so I'll just kind of breeze through this. But what we did find was the DO conditions noticeably changed with operational conditions. We also next slide here. We really look at, we're implementing this combined solution to address generation and non-generation license requirements while accelerating DO enhancement implementation and preserving dam integrity. What we found was that the linear cone valve resulted in consistent increases of DO, demonstrating that the system improved DO when turbines were not in operation. Through all of the measures that were implemented, we're meeting the DO standard. We have the High Rock Dam, and we typically meet the DO standard there most of the time. Below Tuckertown, pretty much 100% of the time. And coming out of the entire project system, it's pretty much 100% of the time, 99.99% typically. So that's an incredible improvement on dissolved oxygen there. And we did have to go, to DEQ to modify our 401 water quality condition. So I think we must be at time here. So that I think that's pretty much the bulk of my slides. But I'll stick around and answer a few questions if anyone has any. And thank you very much for your time. Appreciate it.
you so much, Joyce. And before we get to the Q&A, I was just looking at the number of people on the call. So we have 63 folks on the call, which is a 2025 record for flow attendance. So I just want to give a genuine thank you to all the speakers. This has drawn in a lot of folks. So really appreciate your time today. With that, we'll open it up to Q&A. Again, folks, feel free to type it in the chat, or if you're comfortable, you can just raise your hand and then ask it verbally. Okay.
Katie, I've got a question for Jim and Ty, our first presenters.
Yeah, go for it.
Thanks for the presentation. Just quick question, because you mentioned in the Northeast that it was more common to do quarterly dissolved oxygen monitoring rather than continuous monitoring. So I'm curious how the shift from maybe quarterly to continuous, how have you seen changes in the data with a larger data set, or do you think the quarterly was well represented? Just curious.
I think there's a little bit of pros and cons here. I think part of this is improvement in technology. So we're kind of getting beyond now. I mean, hobos are pretty cheap, and even some of the more robust technology, like Ty was describing, is pretty readily available. But I think there's a number of states in the Northeast for years. The idea of just going out, doing some grab samples, maybe 2-3 times over the course of a month was acceptable. I think once a couple licensees agreed to doing continuous, it just became the trend. So then with regard to the data, it's all about biofouling. So you've got the monitors out there for 2 weeks. I think folks used to think, let's throw them out there for a month, 2 months, 3 months. We'll go get data. But you obviously have to go out there about every 2 weeks, sometimes even more frequently, just depending on the residence time of the impoundment, the temperatures, because what we tend to find is the biofouling at some point will kick in. You get questionable data, and you spend as much time describing what that data means. So hopefully that answers the question. But yeah, like I said, for the longest time, we kind of avoided the continuous. But you just got to make sure that you are dealing with biofouling once you do move to the continuous.
I don't know if I heard that term in the presentation. Would you mind just defining it?
Yeah, you could call it anywhere from just lack of care of your equipment to, depending on where the monitor is in the water column, you just start getting some biological buildup. So especially if you get into a backwater area or stagnant water, it happens rather quickly. That you've got the probe and you've got the sensor on the probe, and once that it's basically almost like it's a growth. Once that growth starts occurring on the sensor, you start getting bad readings. So between that and then the other, I wouldn't call it vandalism. It's probably more just curiosity of what the equipment is. It's always great when you go out there every 2 weeks, you grab your download, and you find out that somebody pulled the monitor out of the water for a week or two, and you just have no data. So that's the type of thing. It's just you have to be a little bit more strategic about placement and just make sure you're maintaining the equipment when it's in the when it's deployed.
Appreciate that response, and I know exactly what you mean because we've had a few of our probes taken out of the water and lost a month's data or more if we're not checking frequently. So thanks for the answer.
Great. Joyce, I have a question for you while we wait for our other questions. You mentioned that you were doing some testing. So I was just wondering if you tested and compared DO at the modified spillway gate compared to the like an existing adjacent non-modified gate.
I don't know if they did it at an existing verse at the same time. I don't know, but they were doing it. They have been doing DO monitoring and continuous monitoring at for a while there. So I don't know if they were doing it just adjacent gates and looking at both gates at the, two different gates at the same time specifically. I don't recall, but I could definitely look into that and get an answer for you.
Yeah, I was just curious. So thank you.
Yeah.
And then I'm still not seeing other questions. So I guess I'll just keep rolling with a couple of my questions. This one will be for the Voith team. I'm just curious, once your mitigation strategies or technologies are installed, understanding they're site specific, is there ever a concern about supersaturation of oxygen downstream? And if so, how do you
Yes,
handle
absolutely.
I mean, our turbines really suck. And so there is potential that you can get oversaturation or supersaturation. We can certainly add valves and things like that to our technology. So that way we can shut down pipes. And if we are doing continuous monitoring, you can tailor the amount of airflow to the needs of the moment. So typically we'll have multiple air inlet pipes, and so we can either throttle them or usually just turn off, a few of those to cut down on the amount of air going in. Yep.
Thank you. And we are just about at time. So if folks have questions, speakers, if you feel comfortable, feel free to put your email in the chat. If not, people can reach out to Kelly Rogers and she can help facilitate that if people on the phone have questions for our speakers after today's call. Speaking of calls, last month we had a negotiation 101 workshop. So if you were not able to attend that and you are interested, that has been recorded, just like this meeting is recorded, and they are available on NHA's portal. So if you have questions on, where in the portal they live or how to access it, again, I'll refer you to Kelly Rogers, but just want to remind folks that these are meant to be resources for you to use in the future. And with that said, thank you again to our speakers. Thank you for everyone who joined today's call. And I hope you have a great rest of your day and rest of your week. Thanks, everyone.
Thank you.
Thank you.
Thanks, Katie.
Thanks,
Thank you,
all.
everyone.
Thank you.
Thank you. Bye.